Welcome to the most comprehensive tutorial about how SAP EWM calculates the latest starting date that you will find in the World Wide Web. Welcome to another video on my channel, and with this one my promise to you is first of all that you will learn something, that I will reveal some of SAP EWM's secrets, so secrets that you will not find in any of the books or in the help text, and last but not least, my promise to you is that I will not make any joke about the term LSD. Just a quick look onto the agenda before we go into detail, and I will start this video with explaining what the LSD actually is and what it is used for in EWM. And the main part of the video will then be about the magic formula, so the formula that EWM uses to calculate the LSD. And this formula is made out of different components. We have three main components, and we will look at each component separately, focus on the details to understand what each component is about, how it is calculated, and then in the last part put this knowledge together to understand how the LSD is calculated. The definition that we get from SAP is that the latest starting date, the LSD, is the latest point in time by which execution of a warehouse order should commence so that it is completed by the due date and time. And this tells us already that the LSD can be used to organize a warehouse and to organize the workload within a warehouse. It provides visibility about time constraints and about the point in time when a specific warehouse order becomes urgent. And it can then, of course, also be used to identify from a pool of warehouse orders the ones which are more urgent than others. And technically, then for the execution, for the operational part, this is used to sort warehouse orders within the queue, to bring them in a sequence for processing so that the most urgent ones are processed before the less urgent ones. And you might have seen that before in the warehouse monitor. For instance, when you see the warehouse order header data, you see the latest date and the latest time. So the latest start date is put together by a date and a time so that we get the timestamp. And as I said before, it is then used to sort within the queues. I give you two examples here. The sorting of warehouse orders holding physical inventory documents. So the sorting within RF queues, for instance. This is also true for sorting warehouse orders for picking or other processes. I just picked that as example here. And you see here that this table here holding the warehouse orders is sorted by the LSD. Amongst other criteria. And another example that I pulled out for you is the sorting of warehouse orders in the context of material flow systems. So this one here is used to sort warehouse orders in queues for MFS resources. For example, cranes in a high bay warehouse that are sorting tasks for pallet movements. And you also see here that the LSD among the priority is used for sorting. The context in which this logic or the LSD as such is being calculated and used is the resource management, and technically that means that it will only be used and only be calculated in case the corresponding warehouse order is assigned to a queue for which resource management is active. So the customizing for this queue needs to set for the operating environment 2, 3, or 5. And this is checked here in the subroutine that the queue type is equal to one of the three constants here, and you see here the value of the variable during runtime reflects the operating environment that I marked above. You know that from my other videos, I mention it here again. All these objects, the technical details that you see here on the slides, that you see on the screen, will be also part of the blog post corresponding to this video. I will put the link to the blog post below the video, and that will have all the technical details, all the object names. So I will not spell them out in detail whenever you see them on the slide. But you don't need to make notes. You will find everything on my website in the corresponding post. And with that, we start the main part of this video, which is a deep dive into each component of what I call the magic formula in the introduction. And this magic formula is given by the SAP help text, and that says that the LSD is calculated by the warehouse order due date minus the sum of the planned execution duration and the planned movement duration. And this is exactly the formula that we will break down into its component within the next 20 to 30 minutes, so that we understand each component before we put everything together to understand the LSD calculation as a whole. There is some pre-knowledge which will help you and which is the foundation of the LSD calculation. And the first topic here and the first important fact is that the LSD is always calculated for each possible resource type which could be used to process the warehouse order later. Now you define different resource types in the customizing, you assign a velocity to those resource types, and as we do not know which of the resource types will later process the warehouse order, we calculate the LSD for all of them and then save only the one for the slowest resource. This is important because we don't know which one will process the order, so we assume the worst case, we save the one for the slowest. And this is done by function module WHO_create, calling then function module RC LSD calc. And within this function module, which is actually our MVP in this video and in general in the topic of LSD calculation, this function module collects all the data which is needed to fill the variables of the formula that I showed you before. And you see in the comment here in the coding another kind of representation of the formula. This is not 100% consistent with the one that I found in the help text, because it first of all uses a different wording and then also a different sorting. But what we see here again are our three components, and the sum, the position is slightly shifted, the sum of the movement and execution duration, which is subtracted from the due date. And what we also see here in the coding as a small hint is that the due date seems to be coming from the wave header. So the first question that I asked myself is what we use and how we calculate then if we do not use waves. I will answer this question in the next minutes. And the movement, the planned movement duration is the distance divided by the resource type's velocity. Everybody who paid attention in physics in school back in the days should remember this formula. And in this context, of course, I asked myself how we actually calculate the distance. And this is also a question that I will answer for you. And the last part, the execution duration, is it seems to be coming from the warehouse order here. This is at least what the comment in the coding tells us. And this brought me to the question how we actually calculate this pick and place duration, so this execution duration, because there is not much more over here in the coding and there was not much more in the help text. So I decided to take the deep dive and look into the coding at this place also. Yeah, now you should better understand what I had in mind in the introduction when I said that we cut the formula into its components. So we know now we have three components for the LSD calculation: the warehouse order due date, the planned execution duration, and the planned movement duration. And I have a subchapter for you now for each of these components, so that we have a deep understanding about how each of them is being derived and calculated. And then at the end, we just put it together and we have the LSD. That's the idea of this video, and that's how we proceed now within the next 20 minutes. We start with the first component of our magic formula, which is the due date of the warehouse order. And this due date is fetched via subroutine getDueDate. We are still in our function module rsrc LSD calc. the one that I called our MVP before. And this subroutine fetches the due date. It does not calculate the due date. It just fetches it, and it is calculated before, dependent on whether you are using wave management or not. And with wave management, the due date is calculated based on the different completion timestamps of the wave template that you are using. And if you're not using wave management, and there are some special cases I will explain later, the planned departure from yard from the warehouse request header is used to calculate the due date. And to start with, which is probably the more common process for you also, is the scenario with wave management. And the first choice is always the pick completion timestamp. You see a wave template option over here with the pick completion timestamp maintained. And this is set to the warehouse task via subroutine set pick completion time here. And this is then taken from there into the due date calculation. If the pick completion date is not set in the wave template attribute, EWM can also work with the pack completion, stage completion, or wave completion date. And EWM considers here not only the timestamp, but also reads the planned duration from the storage process. And this is important to understand, and this is also something that is rarely mentioned in any of the help text. I could not find that anywhere. So if the pick completion timestamp is empty and we are using the pack completion, then EWM calculates backwards against this pack completion timestamp and subtracts the planned duration for the packing step to get then to the due date for the warehouse order, respectively the task here. So in this example here, the pack completion is 9/11, and the due date for that would then be 9/11 minus 10 minutes, because EWM sees in the storage process packing step that packing will have a duration of 10 minutes, and that means the planned pick completion is not 9/11 but 9/11 minus 10 minutes. So picking needs to be completed 10 minutes before the pack completion so that the packing process as such can complete in time. This is shown here during runtime. Don't get confused, I have now a time shift here in the system, but you see here that the pick completion date is then 8/01 and the pack completion, so the planned end was calculated with 8/11, and then minus the 10 minutes from the storage process was the one that brought us this result. And this is true not only for the packing step, you can do that in the same way for staging and loading. The due date as such is, as I said before, then fetched by the subroutine get due date, and that just reads the timestamp and hands it over to our MVP function module that I mentioned before. If you are either not using wave management at all, or the pick completion timestamp is not maintained and you are not using any storage processes, so that the way of calculating that I showed you before depends on the planned duration from the storage process. And if there is no storage process at all, then EWM will exit this way of duration calculation, and get back to the approach that is also used in case you are not using any waves at all. Or third option, in case the wave template option does not have any timestamp at all, so neither pick completion nor pack completion nor stage or wave completion, then it is also falling back to the way of calculating as if it would not use waves at all. And this is based on the timestamp from the warehouse request header, so pretty simple. Planned departure from yard is read from the warehouse request header, and that might actually be set based on the TU. In case your warehouse request header is assigned to a TU, then it will be the planned departure from the TU, which is inherited by the warehouse request header. But the calculation as such is then pretty simple again, and this is, based on my perspective, one of EWM's secrets, because I did not read that anywhere in any help text. If you found one, please add it here in the video description. But I found it later in the code. And here you see the comment also that the duration of the following process steps is subtracted from the planned goods issue time. That makes a lot of sense, right? So picking should not complete when the goods leave the warehouse. Picking should complete so that there is enough time left to pack, stage and load the goods. And that also means I do not take the planned departure from warehouse as the due date, but rather planned departure minus the time that is set in the storage process for loading, minus the time that is set for staging, minus the time that is set for packing. And that is then the pick completion date. And I found that to be very smart actually, because you don't want to set the due date for your warehouse order based on the planned departure from yard. You rather want to set the due date based on the planned departure minus the time that you planned for loading, minus the time that you planned for staging, minus the time that you planned for packing. And that is then the date and time where the picking should complete. And this is the due date for your warehouse order. And from there, you can then calculate backwards what we see in the next part of the video, the planned execution and the planned duration. And the base for that is the storage process customizing and the planned duration time in the storage process customizing. The last part of this chapter is a special case, which is a physical inventory document, respectively the warehouse orders belonging to these physical inventory documents. And those documents do neither have a wave nor do they have a warehouse request where they are assigned to. So the planned count date is the one which is used as the due date in this case. So it takes a role similar to the planned departure from yard. And this planned count date can be provided manually during the creation of the physical inventory document, for example, in the PI.doc create transaction over here, or in any of the other transactions or reports where you can create physical inventory documents in EWM. This closes this first subchapter of the main part with the calculation of the due date. I guess you understand now how it's being derived in the different scenarios with, without, wave management and so on. And we now have the first component of our formula. We know now the date which is being used to subtract then the planned movement duration and the planned execution duration. And this is exactly the next thing that we will do now, the deep dive into the calculation of the planned execution duration. The definition that we get from SAP in the help text is that the planned execution duration is taken from the warehouse order. And unfortunately, this is all I could find, at least in case we are not talking about the context of labor management. Now, there is a lot more details about how this is being calculated with labor management being active, but I decided to take labor management out of scope of this video, just assuming that most of you will not use it and that the calculation differs considerably in case you are activating labor management. So I might do a separate video, but for this one I decided to take it out of scope. And without labor management there is not much in terms of details and explanation in the help text. So I decided to take the deep dive here. And the execution duration, which is also called pick and place duration in the comments in the coding, is fetched via subroutine get pick place duration. And the subroutine simply reads it from the warehouse order, and the warehouse order gets it from the warehouse task. And for the warehouse task, it's being calculated at different places in the customizing. And we will now look into this in detail and break down this execution duration into its pieces. And the first piece of the execution duration is the preparation time for the warehouse order. This is pretty simple. You see here a screenshot from the warehouse order creation rules, and we can provide a constant value here for the WOCR, which is then inherited by the warehouse order which is using this WOCR. This is a constant for the whole warehouse order, and this is then added to the execution time of each of the warehouse tasks within the warehouse order. And we now look into the calculation of this execution time for each warehouse order, which is sitting in the customizing, where it is sometimes called extract time. When we look in the coding, it's sometimes called reach time. But at the end of the day, it all refers to the planned execution duration. Yeah, and this planned execution duration is nothing else than the time that it takes to grab something from the source bin, placing it into the pick HU, and later put it from the pick HU to the destination bin. Now that's the execution time for each task. And you see later in the video that this is being calculated in the same way for the movement from the source as with the placement to the destination. But you can also see that you can use, for example, different bin access types, because in the real world, usually it takes more time to grab it from the source, put it into the pick HU, than later to put it from the pick HU to the destination. Usually you place a full pick HU somewhere, which takes considerably less time than picking it from the source. But you can use, for example, different bin access types. We will see that now in the next part in the customizing. And this customizing is a great help text, by the way, so you should spend some time reading that. I might even do a separate video for a deep dive about what you can do here to calculate or define the calculation of the extract time. To simplify it a little bit for you now, you have a key that you can define in the customizing, which consists, besides some other values, of the bin access type, whereas process type category, unit of measure, and a parameter from the product master data. And based on this key, you then define a constant time. So for each warehouse task that matches the key, you take this constant time plus the variable time, which is the time given in the customizing multiplied with the quantity from the warehouse task in the given unit of measure here. So for this example that you see here with a constant time of 10 and a variable time of 5, I show you now an example for a warehouse task with quantity 10. And the reach time is here first calculated for the source bin. We have here our constant from the customizing, the 10. Then we have the 50, which is 5 times 10. So the variable part from customizing times the quantity of the task. I told you I have a task with 10 pieces. So the sum for the source bin is 60. And as we have only one record in customizing, which matches both of the bin access types, we have the same again here in subroutine reach time det for the destination bin. And you also see here that it calculates the total. So for our task, given the customizing that you saw before and the quantity of 10 in the task, we have 60 plus 60 is a total of 120. And I mentioned before that you could, of course, create different records in the customizing to reflect that usually the placement to the destination takes less time than picking from the source. This is again our example here. We had the preparation time and the warehouse order creation rule. Then we had the customizing with the constant time and the variable times. You see that our warehouse order has 2 tasks actually. So each of the 2 tasks has 120 seconds here. And then we have the 7 minutes from the header. That means we have 2 times 2 minutes for the task, which is a total of 4 minutes, and the 7 minutes for the header. So we end up with a planned execution time on warehouse header level of 11 minutes. So second part completed. We understood how the due date is being calculated. We understand now how the planned execution duration is being calculated. And the next stop, so the thing that we add on top of the planned execution duration, is the planned movement duration. And those two together are then subtracted from the due date, and then we have our LSD. So let us look into the planned movement duration now.
Sorry to bother you one more time, Hendrik again forgot to remind you about hitting the subscribe button. Please make sure to do so. It will motivate him to create further videos, and you'll be notified about any new releases.
Okay. Second part completed, and we understood now already how the due date is being calculated and set in the different scenarios, and how the execution time is being calculated. Now that was a time that the operator needs to grab from the source and drop to the destinations. What we have not done yet is to calculate the time that the operator needs to travel between the different positions that he or she needs to visit to complete the tasks. So physically, that's the operator taking at the starting point of his or her area in the warehouse some kind of a pick HU, a crate, a pallet, whatever, and then sitting on his or her forklift or hand truck or just walk to the first position where he needs to grab something, to the second one, third one, up until the full warehouse order is completed. And logically, that is EWM starting with the starting point of the activity area and then visiting the coordinates of each and every storage bin that you have in the warehouse order. And this is also what you can optimize actually with the storage bin master data when you assign the sort numbers in the LAGPS transaction, for example, and then try to optimize this with the sorting rules in the warehouse order creation rules. The minimization of distance is always some kind of a variable that you try to use to optimize your warehouse performance and the performance of the operators. And the total calculation of that time is the next thing that we look into detail now in the system, how EWM realized that technically. The definition that we get from SAP for the planned movement duration is that the planned movement duration is equal to the distance times velocity. That is what we know from physics class. The following rules apply here. Distance is calculated according to the bin's coordinates using the Manhattan metric. Velocity is the lowest horizontal velocity from all resource types that are qualified to execute the warehouse task. So it looks like we need to calculate the distance first, and I can tell you already that it will only work if you assign coordinates to the bins and the movement duration second. And for the movement duration, we take the velocity then of the slowest resource type. But let us look into the details. And again, we will ignore the options with labor management. There are some more. We will just look at the two options that we have without using labor management. And there is an old, let's say, default way of calculating. Both of them are called from our MVP, from our function module RSRC LSD calc. And the default option is what I call option 1 here in subroutine get travel distance. And the, let's say, new way of calculating is option 2. And this option 2, there is a separate class calling method getTime for LSD that will only be called in case you activate the travel distance calculation in the warehouse master data and customizing. And there is some fancy algorithm for horizontal, vertical movements with this option 2. I will not go into detail for you for now. It's just important to understand there are two options. The more advanced one can be activated based on the warehouse number customizing. And the main difference between two options are, first of all, the more sophisticated algorithm for the calculation of the travel distance. As I said before, both will only work with coordinates maintained in the storage bins. If you don't maintain any coordinates, your travel distance will always be 0. Second, and I think the most important difference, is that the newer option, offers many different bodies and entry points to implement your own logic for distance calculation. And for the option 1, the default way, I did not find any clean entry point. So I assume that this was the main reason to come up with this new approach. The last main difference that I found is that option 2, so the new way, calculates the travel time right away. So it calculates the distance and considers the resource type's velocity, whereas the option 1, the old way, only considers the distance, and the time is then calculated later in a second step based on the resource type's velocity. The closing remark that I would like to give for the movement duration calculation is that there is indeed one customizing node called define planned duration of movement in the warehouse, but based on my analysis and my research, SAP does not seem to use that at all for the movement duration calculation, but rather to set planned completion timestamps for warehouse tasks in case you are neither using warehouse requests nor are you using waves. So it's not interesting for us in this context, but in case you found a way to use that somehow in the context of planned movement duration calculation, feel free to send me a note, write something in the comments. I would be curious to look into this. Congratulations, you made it, almost. we understand now the three components for the formula, for our magic formula. And the last and final step is now to put that all together to calculate the latest start date. And I promise you it's pretty easy. So let's wrap that up here. A last look onto our formula, but you all should know that by heart in the meantime. So let's calculate the LSD. And this is finally done by the subroutine modify LSD, which is called by our MVP here. And this subroutine is then responsible to write the LSD into the warehouse order tables for all resource types. And the first thing that the subroutine does is to calculate the travel time in case you used option 1 before for the travel distance and travel time calculation, because remember I told you that the travel time is only calculated in case you're using option 2 right away. With option 1 you only calculate the distance and travel time then in this subroutine. The result is then added over here to the planned execution duration, so planned movement plus planned execution, and then you have the total duration of warehouse order processing, and this total duration is then handed over to the calculation of the LSD, which is, again, small hint here, a little bit different with labor management, but we ignore that for now, which is here then handed over to function module resource timestamp subtract. And you see here, this is the parts of our formula. So the due date is coming here again, and then the sum of execution and movement duration. And this function module then finally returns the LSD. And now we have it. This LSD is then written into the table for the resource type warehouse order mapping before the warehouse order is being executed. So technically that's table SCWM WORSRCTY, and the LSD is also saved in SCWM WHO. I see that here again on the top the warehouse order header table with the LSD being saved, and on the bottom the table where EWM stores the warehouse order details for each resource type, which is here having the same LSD, obviously, than the warehouse order header table. Yeah, and with that we finally have our LSD. We got the last part of our formula, we put everything together, and now we have saved the LSD in the warehouse order header. And that mainly was the objective for this video, to explain, to understand how the LSD is calculated, but I promised before that we will close with a little bit of additional party knowledge, and that's of course what you get now. And the first area is the production material requests. So we are leaving the traditional world of warehouse requests, deliveries and so on, and for these PMRs I did not find any way for LSD calculation in the standard, apart from one fallback class, which is called for one body, where the LSD is calculated based on the requirements date from the production order. But this is something that I will tackle in my next video, where it's all about how to enhance the latest start date calculation. And I do assume that at some point there might be some more options with waves coming for PMRs. I think SAP announced something like that. So along with the waves, there might be some additional options. And the last point that I would like to tackle here is something that I found for the pick and pass process. And here SAP has a very sophisticated approach where it uses it first calculates the last warehouse order in the chain, and then calculates the duration for this warehouse order, and then sets the due date for the next warehouse order, so the previous one in the chain, to the starting date of the last warehouse order in the chain. So based on this, it just takes all the pick and pass activity areas and lower level warehouse orders in a sequence, and based on this calculates then the LSD for the first one at the end. this is again something we might look into detail in a different video, not something for this one here. Yeah, and with that we are at the end of this tutorial. Just a quick summary. I started explaining what the LSD is, where it is used for, mainly for prioritizing and sequencing warehouse orders within queues, to organize work, to make sure the most urgent ones are processed before the less urgent ones. Then we looked at our magic formula, broke it down into its separate components, tried to understand each of the components, and then finally used those components to calculate the LSD. And with that we can close this session. I hope that you could learn something. I hope that the content was helpful for you. I hope that you are looking forward for the next video, where I will focus on how to enhance the LSD calculations, or how to enhance the separate parts that we looked into today in order to come up with your own custom logic for calculating the latest starting date. Until then, I wish you happy learning, wish you a good time in the projects, and hope to see you again with the next video here. Thanks and goodbye.